So now what we'll move on to is how to implement both the modulation and equalization using DAC-based transmitters, starting first with some examples of current mode DAC-based transmitters. So in order to understand that, let's first look at a simple current mode DAC transmitter example here, where basically the total DAC output current from this differential current mode driver is going to equal to N times the ILSB element here, where N is equal to 2 to the capital N, which is the resolution of the DAC, minus 1. And how we get the different output symbol levels, signal levels from this DAC is basically by steering a current equal to X times ILSB between the differential outputs, where X is an element between 0 all the way up to the maximum code of little n here. So for an example, for a simple 4-bit current mode DAC-based transmitter with a peak-to-peak voltage swing of 1 volt differential, that would require 20 milliamps in a 50 ohm system total here. And if we set X equal to 0, then basically what I would get is 100% of the current flowing through this resistor here, which would realize a minus 0.5 volt signal at my receiver input. By stepping the code with an LSB of 4/3 milliamps, what I can see is I can get a voltage step equal to about 67 millivolts at the input of my receiver, all the way up to code 15, where now I'm steering 100% of the current basically through this resistor to realize the positive output, maximum input of my receiver here. So this is conceptually what we're trying to do with the current DAC-based driver. Now, how do we actually typically implement that? Well, the simplest way to implement that is with a binary weighted current mode DAC with binary weighted elements as shown here. This is very simple because we don't require an encoder. The serialized output of the DSP can simply drive these differential current mode elements here. Unfortunately, though, there are both static and dynamic nonlinearity issues associated with this driver. From a static perspective, essentially the worst case consideration is I need my MSB current source to match the sum of all of these other current sources with an accuracy within 1 LSB in order to ensure that I do have a monotonic transition when I have an MSB transition. If I do not satisfy that, that can result in a very large dynamic nonlinearity during the MSB transitions, and also with a smaller impact at the MSB -1 and lower bit transitions here with the simple binary weighting. So this is what I would get with a static DNL characterization of a typical 100% binary weighted DAC. There are also some issues from a dynamic perspective. So for instance, if we consider the case for this 4-bit example, where I am initially sitting at code 7, which is the minimum absolute negative output voltage here. And let's say I want to switch to code 8, which would then be just a stair step up to the minimum absolute positive output voltage here. So here, I'm at code 7. And during the dynamics, let's say I have the worst case skew where all of these bits transition early, but unfortunately the MSB bit here is still delayed with its original value. Now, as you can see, this is going to result momentarily in the actual maximum negative level being transmitted at the output, this extremely large glitch, until finally, basically, the MSB occurs and we get the desired minimum absolute positive output signal level corresponding with code 8. So this, potentially can cause some issues, in terms of deterministic jitter at the output of our transmitter. So we have both static nonlinearities and dynamic issues associated with simple binary weighted current DAC. Now, the extreme solution to that is to use 100% thermometer weighted current DAC, which is basically going to utilize 2 to the n minus 1 unit current sources. For our 4-bit example, that would be 15 unit current sources. And these are controlled in a thermometer encoded manner that's going to guarantee that it is inherently monotonic. It will also result in relaxed matching requirements. Basically, if you can get half an LSB matching, you're going to get a DNL. Less than half an LSB is illustrated with this much improved DNL results shown here for the same resolution. Also with thermometer encoding, ideally this glitch issue goes away. So for instance, with code 7, I have 7 of these thermometer unit current sources enabled. And if I just step to code 8, well, it's just a matter of activating another one. So I should just get just the ideal stair step response as shown here. But unfortunately, this does result in significant hardware overhead, in that I do need to perform somewhere in the system a binary to thermometer encoding, which results in a lot more wires. So for instance, binary 4 bits is 4 wires, basically. Now I have 15 wires. Maybe I could live with that. But again, typical transmit resolutions are 7 bits, and I can't necessarily live with 127 wires. So, basically you get a large increase in pre-driver and wiring area. So generally 100% thermometer weighted current DAC is not practical. So what's typically done is what's called a segmented current mode driver, where only the most critical, basically most significant bits are being weighted in a thermometer manner. And generally the majority of the other bits, the LSBs, are weighted in a binary manner. So for instance, again, dealing with our 4-bit example, this shows an example where the lower 2 bits are weighted in a binary manner. But then the upper 2 bits, instead of having 2 binary weighted current sources, instead there are 3 thermometer weighted current sources as shown here. So typically the nomenclature to denote a segmented DAC is we have 2 numbers. The number of thermometer bits first, plus the number of LSB binary bits here. So in this case, it's 2 plus 2. In this reference, they actually have a pretty extreme implementation where actually the 8 MSBs are implemented in a thermometer manner, and the 2 LSBs are implemented in a binary manner. So with that, they can achieve very good nonlinearities here, DNL performance. And of course, this also results in a reduced output glitch. You still get a little bit. So again, considering the pathological worst case, where I would be sitting on code 7 here. And the worst case here would be that these guys transition here early. So I still do get a glitch at the output, but it's much smaller than before. And when I finally get the correct MSB settings, I go to my desired output level here. So as we'll see when we look at some real examples, most wireline DACs are going to be segmenting, the 2 MSBs or maybe 3 MSBs. That's typically what is being done. Another issue with a current mode driver is code-dependent output impedance. Now, Ideally, in a current mode driver, the output impedance is dominated by the passive termination resistors because the actual current source segments are high impedance. But we do know that the real transistors do have a certain output impedance, which can be represented with a certain LSB segment, small signal output resistance here. And then based on the number of codes that are activated, I have on either the left side or the right side a certain parallel combination of, let's say, the dependable passive resistance in parallel with the transistor impedance, which unfortunately does vary with the code setting here. So for instance, let's say if we have a typical 50 ohm system, considering that we have 50 ohm transmit side termination in parallel with the 50 ohm channel, that's an equivalent load resistance of 25 ohms for this simplified equivalent circuit model. And let's say we have a typical 7-bit resolution here. And let's say that each segment here has a relatively high resolution of 25 kilo ohms. But when I put all these in parallel, it drops basically all the way down potentially to 197 ohms, as shown here. And of course, this is going to vary with this is going to display some overall code dependency here. So you can see versus the code, the actual, let's say, for a given code, the actual inside resistance and the P side resistance varies kind of in opposite manner. When you look at the parallel differential resistance, you get the following characteristic here. And basically, from a nonlinearity perspective, what this is going to result in is effectively some third order distortion at your output. Now, luckily, this is generally not too bad. So as we can see here, the third order distortion is on the order of minus 60 dBs, which is typically much less than, let's say, the target. If we map this to a target SNDR perspective here, this is typically much less than the let's say 30 to 35 dBs of SNDR we're targeting. So it's something to keep an eye on, but generally this isn't too big of a concern. This is more a concern in very high performance RF DACs, if you will. But for wireline, at least right now, I would say it's not that big of an issue. All right, so let's look at some examples of high-speed current mode transmit output DACs. Starting with this 224 gigabit per second PAM4 implementation, which we talked a little bit about earlier when we talked about the high-speed serializers, but here we're focusing on the DAC implementation. So in this transmitter, the DSP is going to be implementing a 9-tap FFE, and basically the output of that DSP is going to be a 7-bit DAC code, which is going to control this 7-bit DAC-based driver. So if you look at how the DAC is actually architected here, what you can see is that we have 4 LSBs, which are binary controlled, and then 7 thermometer segments, which would basically map into 3-bit thermometer codes here. So again, that's for better linearity. And in each of those slices, again, this is an output multiplexing driver. So each of those slices, so I guess you have a total here of 11 slices, they all have the pulse generators. They all have the scaled version of the output drivers, which again, do current summation at this output network, which, as we discussed previously, has a 7th order LC filter output network here. Now, due to this DSP implementation, you can configure the DSP to support a PAM4 mapping or even a PAM6 mapping. So you can see the corresponding eye diagrams both at 224 gigabits per second. There's better margins with the PAM4i here, but the PAM6 is working at a lower baud rate, which in their implementation actually, resulted in a pretty good reduction in the transmitter improvement in the transmitter energy efficiency. Here's another current mode 224 gig PAM4 DAC transmitter, which we looked at earlier because it has an interesting serializer. So this again is doing output multiplexing. Now, from the DSP perspective, this DSP is implementing a 5-tap transmit FFE. So the output of the DSP is basically the 5 bits that are transferred. I'm sorry, the 5 taps output, which is being transferred to the output DAC here, which is basically implemented with 4 binary LSB segments, and then 3 MSBs, which are mapped into 12 segments. So it's a little bit of a specialized mapping that they have here to basically balance some of the area of the segmented output DAC here. So this is a current mode implementation. It actually uses a pretty similar implementation to what was done on the previous slides. Both of them are effectively using this tailless current mode driver, where basically the source of the current transistor is being switched with the actual switch transistors controlled by the pulse data here. Because this does a more higher output multiplexing factor here. You can see that not all 8 of the transistors are hooked up to the source, but it's done with 4 parallel transistors here that are being activated to distribute this capacitance here, basically. But overall, this has pretty good outputs at 224 gigabits per second. So those were some examples of current mode DAC-based transmitters. Now let's look at some voltage mode DAC-based transmitters. So this here shows an example of a 56 gigabit per second high swing voltage mode DAC-based transmitter based on these 2-to-1 output multiplexing driver segments. So as we can see, what's coming out of the DSP is going to be implementing a 5-tap FFE here. And this DSP is basically going to be operating at 1/40th rate of the actual final symbol levels. So that's why you can see 40 parallel output bits, and that's passing through the 5-tap FFE. Then that comes out at the 7-bit resolution of the DAC. So these essentially 40 codes at 7-bit resolution are then serialized with a 40-to-2 mux chain here before they hit the final, let's say, output segments where the final 2-to-1 multiplexing is being done. So this is a voltage mode DAC here, but you can see that the segmentation is done in a somewhat similar manner. For this 56 gig implementation, they have 5 LSB bit binary coding and then 2-bit MSB thermometer coding. And they're able to achieve a 0.9 volt peak to peak differential output, which, when they apply the TXFIR, they can get a very clean output eye, even with this output multiplexing scheme here. Here's another 56 gig PAM4 voltage mode DAC here. Also, if it's long reach, generally we're going to be using SST high swing drivers as shown here. We actually looked at this example earlier because it used an interesting level shifting pre-driver here to implement the high output swing. Here, what I'd like to point out is that the DSP is implementing a 5-tap FFE, And you'll also see some consistency. These are two different companies. Some consistency in the implementation. So this is also a 7-bit DAC with 5-bit binary and 2-bit thermometer with a 1-volt peak-to-peak differential output swing. With, again, by level shifting the ground of the final pre-driver logic here, they can avoid overstress of the PMOS switch transistors at the output. Here's a little bit higher speed implementation, 112 gig PAM4 SST 7-bit DAC transmitter. So this is a double the data rate at 112 gigs. So you can see that they're using a higher 6-tap FFE or FIR filter here. Now this is also implemented at the 40th rate. So basically you have 7-bit code with 40 parallel implementations of that at the output of the DSP that then passes through the serialization network here, which is in each slice of the DAC here, at least the final 8-to-1 serializer here. So this is a 7-bit DAC implementation here. Unfortunately, this design didn't disclose the segmentation. But what we can see is that this also has a high swing output driver as shown here with the final serializer operating at quarter rate, which is also using a similar tailless current mode multiplexer that we showed earlier and that other analog voltage mode output driver. This design here also has some details on the closed loop control to get better performance of this serializer. You can see that they have a replica bias scheme that better dials in the actual impedance of this PMOS to get the desired output swing of this pre-driver here. So you can see that they get pretty good results for this 112 gig output driver. Now, one thing is that with these DAC-based transmitters, generally these high swing voltage mode drivers, which have both PMOS and NMOS transistors, have higher output capacitance. And, we have not seen any voltage mode implementations, at least for DAC-based high long reach SERDES at the 200 gig space. So far, we've just seen it basically at the 100 gig space. And, basically the increased output capacitance is one reason for that. But there has been some high swing voltage mode DAC implementations, just not a full transmitter. So for instance, shown here is a very high speed, 72 sample per second, voltage mode 8-bit DAC here. So this implementation does a very interesting approach where they can achieve 8-bit resolution with only 23 DAC elements. So that's a significant reduction in the number of elements. And that's basically by using both what they call these A segments and the B segments. So these B segments here are going to be sized to achieve 8x higher resistance, or 8x lower strength, basically, than the A segment. So, for instance, this shows their A segments with a certain, basically, header strength and switch strength and series resistance, and then the B, which has significantly more series resistance. And to get better matching, what they have is a combination of these header and footer devices with analog tuning being employed here to dial in better linearity between these 8x sizing between the A and the B segments. So this was not a full transmitter. This was just a DAC implementation, but they do have an on-die memory here, which, based on programming the memory, they can emulate PAM4, PAM6, PAM8, and even OFDM modulation. With this high swing driver output, they can have a pretty good 0.92 volt peak to peak differential swing. So these are some details of this high-speed voltage mode DAC here. So you can see that, again, it can be configured to output at 72 samples per second. That's 144 gigabit per second PAM4. But if you push it all the way up to PAM8, that's potentially 216 gigabits per second. At least that's what they demonstrated here. You can see, though, that obviously the SNR of these PAM8 eyes is somewhat degraded. And of course, you need higher SNR to support the modulation. So there's a question of whether this is going to work, but you can at least see that the transmitter can output that. From a static perspective, you can see that they get pretty good INL and DNL performance here, all less than LSB. And they also demonstrated some interesting OFDM modulation here with actually for 64 QAM constellation here, the power is pretty good, 1.36 picojoules per bit. And as I kind of alluded to earlier, this SNDR for the 64 QAM constellation is actually better than what they get for this PAM8 here, which demonstrates some of the jitter robustness associated with this lower symbol rate OFDM. Now, that being said, this bit error rate still is a little marginal, but overall, this is interesting results.